Okay. This chapter is entitled Chemical Bonding, the Ionic Bond Model. But there's really more to it than that. It does talk about bonding, of course, but that's really a prelude to writing, naming, and balancing compounds, and then eventually writing chemical equations. So this is the authors lead into that topic, or those topics. All right. So let's see, where are we gonna get to? Chemical formulas, okay. Binary, this is where we name compounds. And that's it for this chapter. All right. What is a chemical bond? We sort of have an intuition about it. Well, some of us do. Chemical bonds hold atoms together. And they hold them together with such strength that when you're bonded to another atom and you come close to some other group that's bonded together, the strength of their attraction is better than half the time not strong enough to tear your bonds loose from within the molecule. There's a name for that. The intramolecular forces are the ones that hold the molecule together. The intermolecular forces are the ones between molecules. So we'll come back to that later. This attractive, in its simplest form, the attractive force that holds two atoms together is the definition of a bond. But it goes deeper than that, and it starts to subdivide because we're trying to understand why atoms bond to one another. That understanding will lead to the ability to predict outcomes in reactions and to create new reactions that you hadn't considered before. If you can understand why they bond. It's not just cookbook anymore. Like, we're not alchemists. We're not just mixing stuff together to see if we can make gold out of lead. Bonds can be subdivided into, well, before I do that, think about two atoms when they approach one another. And it doesn't matter what they are, because all atoms have a common structure. You know, they have a nucleus, right? And they have this electron cloud out here. Think about what happens when they approach one another. What do they see first? Electrons. So the electrons are responsible for the bonding. Now, you can have a bond formed when electrons move entirely from one atom to another. When they do that, you create ions, right? We didn't talk about ions, you didn't. Okay. So if you have sodium and you have chlorine atom over here, sodium's got 11 protons and chlorine has 17. Well, sodium also has, if it's neutral, it also has 11 electrons, right? 11 protons, 11 electrons. 17 protons and 17 electrons. So that's a nonmetal, this is a metal. Metals tend to lose electrons. They have more mobile electrons in their outer shell. That's why metals conduct electricity, they conduct heat. And the nonmetals, on the other hand, tend to attract electrons to themselves. So this sodium being in the first group, alkali metals, we know that those always form +1 ions when they form ions at all. So this one electron from here transfers over here. Now this has an extra electron. I need to write bigger because the resolution in this thing is horrible. Let me do that. Okay, so when we transfer an electron here, we get 18 electrons, which means you've got 17 pluses, 18 minuses. That's where the negative charge comes from. It's a balance. 11 electrons here, it lost one. So now it has 10 electrons. Well, it still has 11 protons. So 11 positives and 10 negatives means this one is now positive. Okay, so that's where the charges come from. And when you do that, the attraction between these two is purely electrostatic. It's just positives attract negatives, that's it. All ionic compounds are that way. And that is the ionic bond. And in order to get that, you have to transfer an electron or more, one or more electrons, completely from one atom to the other. There can't be any halvesies on this. The electron goes somewhere else to produce the ionic bond. On the other hand, if you've got two nonmetals, like I said before, they tend to attract electrons to one another. So how do you get a bond between two nonmetals? Well, they have to share. And that happens. They do share electrons. For instance, if we have, let's just take two like atoms, oxygen. Right? They attract electrons to themselves, but they're the same type of atom, so they attract equally. So in order to form a bond here, they have to share electrons. Now, what is okay, let's start with their structure, their electronic structure. I know that gives people fits, but it's useful to understand that. So the structure for oxygen with 8 protons and 8 electrons would be the same for both of them. So this will be 1s2, 2s2, 2p4. 8 electrons. Okay. Now, what would be the nearest noble gas to these? Neon, right? So neon would be 10 electrons. Neon would have 6 here. And that would be a complete orbital. To have 2 electrons here and 6 there, be complete. No more coming, no more leaving. It's perfect. Think of it in those terms. Oxygen wants to look like neon. It wants 2 more electrons to complete that shell. So how's it going to get 2 electrons from oxygen when it wants 2 electrons? Well, they share. They share 2 electrons between each other. And to do that, when they do that, they think, each of them thinks it looks like neon. Like they both go to the same beauty shop. And now oxygen thinks it's neon, and this oxygen thinks it's neon. And you get a bond between them. In fact, you get 2 bonds. Right? If this one shares 2 electrons, and this one shares 2 electrons, then one bond is 2 electrons. So they have 2 of them. We'll talk about that a little more in a minute. Okay, so we call that a covalent bond. Now I gave you one there where the oxygens share evenly. So the electrons spend an equal amount of time between each oxygen, but it doesn't have to be that way. electrons can be shared between two atoms that have a different strength of pull on the electrons. So the electron may spend a little more time around one atom than the other, but they still share the electrons. Okay. The nature of the chemical bond was so important that this scientist, Linus Pauling, took everything that was known at that time in the late 40s, early 50s, everything that was known, all the research on that pertained to the chemical bond, and pulled it all together. In the sciences, there are two types of people. They're the analyzers and the synthesizers. Analyzers take stuff and just tear it apart, try to pick out pieces and understand the pieces. But every once in a while, you need somebody that's adept at pulling everything together and making sense of all those pieces. And Linus Pauling was one of them. In fact, he did it so well that he got a Nobel Prize in chemistry for it, the nature of the chemical bond. Now, we can't go into all these details right now, and some of the conclusions that he drew have kind of morphed over the decades, but he did pull things together and got it started toward a better understanding of the chemical bond. Okay, this is probably a rehash of what I've told you about the ionic bond already. You need a transfer of electrons, right? At least one, sometimes more. And the compound that's formed is known as an ionic compound. Remember, compounds have to have two or more different elements. Okay, and in an ionic compound, it's absolutely essential that they be very different. In other words, the metal, the further to the left the metal is on the periodic table, compared to the non-metal on the other side, the further apart they are, the stronger that bond is. Okay, that's an ionic compound, and it's purely electrostatic. The covalent compound is actually called a molecular compound. And the reason for that is, as compared to an ionic, and I got to write bigger, don't I? Keep forgetting. Got poor resolution here. Ionic versus covalent. Okay, this produces an ionic compound. This produces a molecular compound. Okay, so what's the difference? Well, the ionic compound is in your imagination. Sodium chloride, for instance, is going to be sodium ions and chloride ions. But they're individual ions. They have their own identities. The only reason they're there is because positives and negatives attract. But in that salt that you just spilled on the table and you're looking at it with magnifying glass, right? Everybody's done that, right? Some people have, oh, good. I don't think I'm weird, the only one that does that. You see little cubes, don't you? Those cubes are there because of the way sodium ions and chloride ions arrange one another. This sodium ion is surrounded by chlorides. Right? But these chlorides are also surrounded by sodiums. And that's only in 2 dimensions. It goes off in 3 dimensions. And actually, if you look at one sodium and another chloride, you could just as easily write this compound as 6 each. Because for each sodium, there are 6 chlorides around it. And for each chlorine, there are 6 sodiums around it. So these ionic compounds are really written the simplest whole number ratio of the ions. Okay. Now, I told you all that in order to make the comparison between that type of compound and the molecular compound. The molecular compound, where you're sharing electrons, those atoms are bound together in such a way that they form a single unit. That is the unit, not just an imaginary ratio of one sodium and one chloride. For instance, water will have an oxygen and two hydrogens. Okay, and it is a separate entity from all other water molecules. It's not like there's an oxygen ion and a hydrogen ion, and they just kind of mix around. No, this bond is between that oxygen, that hydrogen, same on this side, and that's a single entity. That's a molecule. You can't say that about ionic compounds. There are no molecules there. They're individual ions. Okay. Now, I don't know if I said this before, but I probably have. Nature just does what it does. We try to wrap our brains around it, try to figure it out. And this is one way that we're doing. We subdivide into ionic and covalent compounds. But actually, in nature, it's a broad spectrum of bonding. Right? You could have extreme ionic over here, and then extreme covalent over here between like atoms, like oxygens and nitrogens. All the diatomics are that way. Right? The same element on either end of the bond, so they share electrons equally. But in between there's a spectrum. And you have ionic character, you have covalent character, and then you gradually shift along that spectrum toward more ionic, but it's still covalent, more ionic. And at some point, you sort of say, all right, so the electron's spending so much time over here on this side, we've got an ionic compound. Okay, it's in a spectrum. So that's what we're saying here. All bonds have some ionic and some covalent character. That's what that means. It's all on a spectrum. And it just depends on the nature of each of the atoms in the compound as to how much ionic character they have and how much covalent character they have. It's also important to realize that not all the electrons that surround an atom are involved in the bonding. So you have what we call valence electrons, those in the outer shell. They're available for bonding. And then everything else inside is called the core electrons. They never participate in bonding. Now, they do influence the character of the atom. That's true. But the bond itself is between those valence electrons, those outer electrons. And if we put oxygen back up here, okay, these are the valence electrons. In the highest principal quantum number identifies the valence electrons. So oxygen has 6 valence electrons. How about fluorine? With 9 electrons. So it would have 1s2, 2s2, 2p5, right? 5, 6, 7, 8, 9. So it would have 7 valence electrons. And if you look at the old system of identifying columns, that's why that Roman numeral 7 is up there. That identifies the number of valence electrons. That only works for the representative elements. This group, that group, and these 6 groups over here. Once you get down into here, it's a little iffy. But the representative elements here and here, it works really well. And that's where the concept of the octet comes from. because in order to complete this one, it only needs one more electron. And it's got 2 + 6 is 8. It's got an octet. Okay. Oh, and I didn't notice I was staying on track here. The Octet Rule. That's what these elements are trending toward. They want that octet because it makes them look like a noble gas, and the orbitals are complete. They want complete orbitals any way they can get them. If they can get them by ionic bonding, great. If they can get them by sharing electrons, then they'll do that. All right. Transfer, you got to have a complete transfer of electrons from one atom to the other. The valence electrons I mentioned earlier. These valence electrons are found in either the S or the P subshells in the representative elements. We can expand the concept of valence electrons to these transition elements, but it doesn't work quite as well. Okay, so we'll have to hold that topic till later. We'll focus on the representative elements because they're better behaved in that respect. Okay. Now there's a chemist, an American chemist named G.N. Lewis. And he thought drawing out the electronic configuration of an atom was too cumbersome. He wanted a more convenient way to represent these valence electrons so that he could bring two symbols together representing atoms, and the valence electrons will be identified around there. So you could say, okay, how are these going to interact? Let's see, you can count the number and where they are around this symbol and treat that as an atom. So you can think through a problem more quickly and easily, rather than having all that S's, P's, and electrons scattered around. So he invented this notation, which gives us the Lewis symbol, or the Lewis dot structure. And the dot stands for the electron. Okay, so all you have to do is draw the symbol, and then you position the electrons around that symbol, however many valence electrons there are. You seen this one before?
I'm pretty sure.
Okay. So let's just take an example, say nitrogen. So nitrogen has 7 electrons, 7 protons, 7 electrons. And we would normally write it like this. 1s2, 2s2, 2p3. 1, 2, 3, 4, 5, 6, 7. Okay, we know these are the valence electrons. Okay? So there are 5 of them. Lewis just took the symbol and he started dotting in either clockwise, counterclockwise, it doesn't matter. 1, 2, 3, 4, 5. Put your singles in first and then pair them up afterwards. So this would be the Lewis dot structure for nitrogen. And it has 5 valence electrons. And if you look up here, that's Roman numeral 5, or count from the left, 1, 2, 3, 4, 5. Nitrogen has 5 valence electrons. So who else has 5 valence electrons? Phosphorus, arsenic. They all have 5 valence electrons. That's why they're in the same group, and that's why they behave similarly in chemical reactions, because of that similarity in their valence electrons. Okay, and you can do that with any of the others. Say all the alkali metals only have 1 valence electron. That's it. That's why they tend to get rid of it. Right? If you get rid of that 1 valence electron, what do you look like? You look like a noble gas. It's really easy just to throw it away. Well, you don't throw it, you transfer it. Okay, so the number of valence electrons for these elements, all you have to do is look where they're located. Calcium is in the second column, it has 2 valence electrons. Okay. Selenium, that's in the chalcogens right there. So it would have, count from the left, that's 6 over. So it would have 6 valence electrons. And for illustration, we're including also where are those valence electrons located. This is selenium would have its valence electrons in the 4th principal quantum. And that's in the 4th period right here. So you just go across here, there it is. Okay. Once we understand how the periodic table is built, then it's easy to write the structures and it's easier to make these, draw these conclusions. And carbon, how about carbon? What do you think its valence number would be? Right? Yep. 4 valence electrons. Okay. Oh, generalizations, right? We can say this for representative elements. Those that are in the same group have the same number of valence electrons. That's true. And they're the same as that Roman numeral. Now, when you did that extra credit, the method asked you for the new Iupac version, right? Just 1 through 18 from left to right. And that's because that's what we're supposed to use. But some of us old timers like the old system too, because those Roman numerals tell you more than these numbers do. The maximum number of valence electrons for any element is 8. Now that's true for the representative elements. Right? Like I said, when you get into the down here, then the system changes somewhat. So we're not going to spend any time in that area right now. We may never get to it. Besides, it messes with our octet rule. And for using the Lewis dot structures, the octet rule reigns supreme. That's where your focus is, using that system. All right, so we did oxygen. No, we did nitrogen. Oxygen, you just add 1 more, right? Because it's 1 to the right. It's got an extra electron. So we pair up another one here. How about phosphorus? Well, it's like nitrogen, so it'll have 5. And fluorine has almost enough. It's just missing 1. So it's got these 6 paired and that 1 lone electron there. Okay. A valence electron is the outermost electron shell. Yeah, that's true. Shorthand method of Lewis dot structure. Okay. So when we're putting these elements together, trying to form compounds using this system, what we do is we say, all right, 2 electrons is equal to 1 bond. Okay. It's always the case. If you have, say, 4 electrons between 2 atoms, then you have 2 bonds, and so forth. Okay. Whenever you see a line between 2 atoms representing a bond, that's always 2 electrons. Okay. I mentioned that earlier. Everybody's trying to look like a noble gas. Okay. We already talked about this, how to form an ion, but I didn't name them. Okay. So the negative ions like chloride, that comes in the category of anions. And the positive ions, like sodium, is a cation. Now, this is not the only cation. Any positive ion would be a cation. Any negative would be an anion. Those are just examples. You can't mess with the protons. What happens if you mess with the protons? You get a different element. Right? You don't have an ion of the element you started with. Okay, so I'm not going to spend any time on this. We know how to make ions. Okay. Where's our chemical symbol for the first one? Potassium. Okay. Right? What ion would form if it loses one electron? First of all, is that possible? Where is potassium? It's over here. Okay. Yeah, it could lose an electron. It's metal. So if it loses one electron, what do you have? Plus one ion. Right? It's all in the balance. You still got the same number of protons, but you've got one less negative, so that means it's a positive one. Okay, how about sulfur? Notice where sulfur is located. It's a nonmetal, so it tends to gain electrons. So how many would it prefer to gain? 2, right? If it gains 1, it's only looked like chlorine. It wants to gain 2 and look like argon. So sulfur would be 2 minuses. Okay. Let's see. Atoms tend to gain or lose electrons until they have obtained an electronic configuration like a noble gas. That's not news. That's it. Now this sodium ion, that is not its electronic configuration. That's the electronic configuration of the neutral atom. Right? This one electron in the 3s orbital says, look where sodium's located. 1, 2, third period. These are all s filling here. It's only got one electron in that s orbital. So that's technically not right. It needs to lose that electron before it becomes that ion. So when it loses that electron, what does it look like? Well, you have to back up one, right? Sodium, you got to back up over here. Now it looks like neon, because that's the electronic configuration of neon, and it has a full orbital. You can't put any more electrons in there. If you take any away, it'll be deficient. Okay. So the question is, which requires more energy? Lose one electron or gain 7? Well, lose 1. That's why sodium tends to, everybody in sodium's family tends to lose 1 electron to become a positive ion. That's their nearest neighbor. They can get to a noble gas by losing 1 electron. Okay. So when you move from left to right, and the old-fashioned group numbers, when you move from left to right, you've got 1 electron here to lose, you've got 2 electrons here to lose to make a noble gas. So that's why everything in the first column tends to be plus 1. Everyone in the second column tends to be plus 2. And then jump over here, everybody in here tends to be plus 3. Once you get here, you're kind of in the middle, right? What's halfway in an octet? 4, right? So you could go either way, plus 4, minus 4. So these folks right in here can actually, they're AC/DC, they go either way. But if you work from on these nonmetals go from the other side. Everybody in this column tends to gain an electron, so that it'll look like its nearest neighbor here. Right? Look like those noble gases. And these would have to gain 2. These would have to gain 3. Now, that's if they were becoming an ion. They would gain those electrons. But if they were actually associating with another nonmetal, they may share. So they could share 3 electrons for nitrogen. And that way it would look like, it would feel as if it had those 3 extra electrons to make it look like a neon. So that's why when you see nitrogen written as its diatomic, right? It's a diatomic gas, right? All these diatomics, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomics. So they bond with one of their neighbors. And it would take 3 electrons from each side to make them heavy. They look like neon, right? 2 electrons here, 2 electrons there, 2 electrons there. How did we get there? Well, look at the Lewis dot structure. Nitrogen would be 5, right? We just drew that one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this one shares with that one. This one shares with that one. And this one shares with that one. That's where you get your triple bond. Okay. You don't need to share those because now count the electrons. 1, 2, 3, 4, 5, 6, 7, 8. This one thinks it has 8. 1, 2, 3, 4, 5, 6, 7, 8. That one thinks it has 8. Now it doesn't have 8. They're sharing, right? But it gives them a fuzzy feeling. We feel like we look like neon now. Okay. We talked about those nonmetals. Now, when these nonmetals combine with metals, then they do form those ions. In other words, nitrogen bound with, let me see, let me make one up. How about sodium? That's a bad example. Yeah, I said that one. But when they do form a bond with metals, they tend to form those ions. Rather than sharing, they actually do gain 3 electrons. We'll have opportunity to look at those a little later. The carbon group, it can go either way. It just depends on its neighbors, whether it's going to gain electrons or lose electrons. Now here's a concept. We'll just throw this one out there. The Isoelectronic Series. And it's based upon that tendency to look like noble gases. So that's where I start. When I'm looking at an isoelectronic series, I start with a noble gas and work my way out. So an isoelectronic series is a group of, it nearly always has ions in it. There may be one neutral atom in there. In this case, there are no neutral atoms in this group. But what is their electronic configuration? Like nitrogen with 3 minuses would be 1s2, 2s2, 2p6. Neon. It looks like neon. Well, how about oxygen? It looks the same. Fluorine looks the same. Right? They all have the same electronic configuration. Now, in this case, we chose to make them look like a noble gas, but they don't have to. As long as they've got the same electronic configuration, then they're isoelectronic. But the series becomes more useful and understandable when we make them look like neon or look like a noble gas. Right? So this one would lose an electron, it would look like neon. They all have the same configuration. And then, of course, you stick neon in there and it would fit in that group. Right? So you look at the neon here, then F minus, O2 minus, N3 minus, or, and sodium +1, magnesium +2. You could even say aluminum +3. Is aluminum in there? Yeah, there it is. Aluminum +3. They all look like neon electronic configurations. Those are isoelectronic series. Okay. I think we're beating this horse just way too long. Let's move on. Is that possible? Potassium +1, what would it look like? If we take away an electron, then it looks like argon. Okay. If chlorine adds 1 electron, it looks like argon. If calcium loses 2 electrons, it looks like argon. So these are all isoelectronic. And obviously, to make those ions, everybody wants to look like argon, and that's argon. Okay. Now, the number of electrons for each species is actually 6, 8, 14, 16, 18. They're all 18 electrons. Number of protons, though, is different for each one. It has to be. If it's not different, then they're all the same element. Okay, so protons will be different, electrons will be the same. All right. All right, we'll indulge the authors for this one. And as long as we don't take too long. Magnesium ion. You can approach this several ways. You can write out the electronic configuration for magnesium, or you can say, what's the nearest noble gas to magnesium? Right? Go backwards, neon. So it needs 10 electrons. 1 S2, 2 S2, 2, 6, 6, 7, 8, 9, 10. There you go. So that would give you the electronic configuration for the magnesium ion. Okay. I've already explained this. Ionic compounds always form between a metal and a non-metal. That's because one wants to give up electrons and the other one wants to receive electrons, so they can both look like noble gases. And the forces that draws them together is electrostatic. Okay, so this is what the transfer of an electron would look like in a Lewis dot universe. Sodium only has 1 valence electron. It's going to get rid of that valence electron, transfer it over to chlorine. So now sodium has no valence electrons. They're all cores, and makes sodium look like neon. So this is neon, and that's neon, electronically speaking. Okay, what about oxygen? Well, if we write oxygen's Lewis dot structure, it's got 1, 2, 3, 4, 5, 6. So let's check that out, be sure. 1, 2, 3, 4, 5, 6. Yep, 6 electrons. Position those around. Like 1, 2, 3, 4, 5, 6. Sodium gives up 1 electron for this pair, and this sodium gives up an electron for that pair. That's why the compound, when you write sodium oxide is Na2O, because it takes two sodiums to balance the charge for oxygen. Same thing with calcium and chlorine. Calcium has 2 electrons to give up. This chlorine only needs 1. This one only needs 1. So now calcium is a 2+ ion because it got rid of 2 electrons. Chlorine each is a -1. So the balance of the charges, to make 0 balance, you have to have 1 calcium and 2 chlorine. Okay. All right. Let's skip that one. Ionic compounds must always be neutral. You have to balance the charges. Now, when you get to covalent compounds, that's irrelevant. There are no charges. So you have to approach it differently. But for ionic compounds, you have to balance the charges. And when you write the compound, you see which group is it in. Right? These would all be +1, +2, +3. These would be -1, -2, -3. And then these guys kind of in the middle. And use the subscript. Remember when I wrote that, Adam told you what these positions were for? This is the number of atoms in the compound. Okay. And it's based upon the charge. Okay. Now we don't have to deal with these two anymore, because we know what the charge is, we know how many there are. So most chemistry takes place without those nuclear designators. Okay, so what kind of compound forms when sodium ion and 3- phosphorus get together? Well, let's see, is that possible? Yeah, 1, 2, 3. Yeah, phosphorus is 3-, sodium's 1+. So it takes 3 pluses to balance that 3-. How about this one? You got a 2+, how many chlorines do you need? 2. Right. 2 chlorides balance that 1 barium. How about this one? Uh-oh, we got an odd and even. How do you deal with that one? Fe 3+ and O 2-. Simplest way is cross multiply. Just put that 2 down here and put that 3 over here. And then check yourself. Right? 3 times 2-, 3 2- is 6-. Right? And 2 3+ is 6+. So they cancel. All right. And how about this one? Pb 4+ and 2-. O 2-. Okay, looks to me like if we have 2 of these, then we can balance those 4 pluses. Okay. So that's 2 times 2- is 4-, balances that 1. So we really only need 2 oxygens in this case. And the charges are balanced. Okay, correct formula for Al3+ and Cl-. 3 minuses, right? 3 chlorides should do it. Aluminum chloride. We haven't named compounds yet. I'm using names. I'm giving them names and haven't told you why. It's on the agenda.
Is it aluminum trifluoride? No.
I'll give you the rules in a minute. Probably should have done that first. Maybe switch my slides around. Let me see. I better check myself, see how far along I am, so I don't run out of time.
because we got several other things to cover here. We are going to get to the rules in just a second. Okay.
Ionic compounds. I alluded to them earlier with the cubes of sodium chloride. Those solid ionic compounds, and most of them are solids, they consist of these positive and negative ions arranged in such a way that they distribute their positive and negative forces throughout the system evenly. They tend toward, in fact, all compounds when they form tend toward minimum energy. So for instance, if we had calcium chloride, right, everybody's throwing calcium chloride out on their sidewalk in the winter, right? That's that extra heat. Sodium chloride works to melt the ice, but calcium chloride's better because it has more ions. Plus, it doesn't damage your concrete. I made that mistake when the first winter I was in my house, my new house. I threw plain salt out there. And next spring, I had little holes in my concrete. I added a patch. Be that as it may, this ratio, I'm putting in the charges, would have a calcium ion here, and then it would have a chloride there and a chloride there. And then it would also have another chloride here and a chloride there. But these chlorides need somehow to get these charges balanced. So that, without going into too much detail, that's why the shape, the macroscopic shape of a crystal gives you clues as to what's in the crystal. A perfect crystal of calcium chloride is called calcite. If you've ever seen it, it's sort of it's like a, I don't know, what do you call this? Parallelogram. It's kind of like that, but in 3 dimensions. If it's like this, then it's hold this constant and you push that one to the side. So it's a rhombus. That's what it is. It's a off-center rhombus, and it's because of this arrangement is the reason it takes that shape. Whereas sodium chloride is 1-to-1, plus and minus. So cube is the most efficient shape for that. I better move on. There's our cube. Right. Now, why are these sodiums so much smaller than the chlorides? Well, in the first place, sodium's only got 11 protons and chloride's got 17. So it's got more electrons to start with, right? Which makes it bigger. But we're going to add an electron to chlorine, and we're going to take one away from sodium, which shrinks sodium and balloons chloride. So that's why the chloride is represented as a bigger ion than the sodium is. And that also contributes to the arrangement here, the way they fit together. Okay, so for these ionic compounds, like I mentioned earlier, NaCl is the simplest whole number ratio of ions in that compound. And that's the way we approach ionic compounds. Simplest whole number ratio, and that's known as a formula unit. Sodium, one chloride, balance the charges with the least number of ions in the expression for the compound. And that's a formula unit. As opposed to a molecular compound where you actually put how many atoms of each is in that molecule, because only then can you have that molecule. But with ionic compounds, you could have like a billion sodiums and a billion chlorides in there. Okay. What term is used to refer to the smallest whole number repeating? Well, we just said the formula unit. I don't know why I keep these slides in here. They kind of insult our intelligence. Okay, the metallic elements that have fixed ionic charge are these. Group 1 is always +1 in ionic compounds. Group 2 is always +2. These are always 3+, and gallium is 3+. I think boron kind of squiggles around simply because it's on the non-metal side of that dividing line. But aluminum and gallium are always 3+. Now we have some transition metals that are fixed charge also, for slightly different reasons. But when we start naming compounds, it's good to know those, because there's a different rule for those as there is for the variable charged metals. So zinc, silver, and cadmium are always 2+. All right. So now we're going to learn how to name compounds. We're going to start really simple. Binary compounds. And we're going to start with the binary ionic compounds. That's as simple as, as simple as you can get. The type 1s, let's see, let me move over here. The type 1 binary ionic compound is made of a metal and a non-metal. That's not nitrogen. That's a non-metal. Okay. Metal, non-metal. And the metal is always fixed charge. Okay, so anytime you have fixed charge metal in combination with a non-metal, you use the type 1 convention. Okay, so what is that? You write the name of the metal just as is. That's the name of the element. So that's why we say sodium. Okay. Then you change the name of the non-metal to make the ending IDE. So chloride instead of chlorine. Right. And that's all you have to say. You don't have to make any reference to the charge on the metal or how many there are here. The guiding principle for Iupac. Right? Did I tell you what Iupac is? Okay. International Union of Pure and Applied Chemists. The guiding principle is, first of all, non-ambiguity. In other words, the name can only mean one compound. When you say that name, it has to be this compound and nothing else. There's no ambiguity involved. And not redundant. In other words, we don't have to say what the charge is here, even though, because we know what the charge is. It's fixed. That's +1. Okay, so those two guiding principles. So let's see, we're going to have some more examples. Well, okay, so we're going to say bromide. If carbon is the anion, then it's called carbide. Right? Calcium carbide. Does anybody here have some old timers, retired miners in the family? They ever tell you about using their carbide lamps underground? They used to go underground with open flames in their carbide lamp. Calcium carbide is that compound. Okay, and when they put some crystals in the little canister in their helmet, and they add water to it. When you add water to that, it produces acetylene, and then you just light it, and that's how you saw your way around. Of course, it's kind of hazardous, right? Because explosive gases and coal dust tend to build up in those tight spaces. So they got away from that eventually, and now they use sealed electric lamps, which are much, much safer. But that's a carbide. And notice we wrote the metal first and the non-metal second as the anion. So that's the trend. The positive ion comes first, the negative comes second, and we change the ending to IDE. And same for all of these. Hydrogen is another possibility, right? When hydrogen is in that second position, it's an anion, and we call it hydride. Okay? So this one would be potassium chloride. This one would be magnesium bromide. Even though there are two of them, we don't have to say two, because the balance of charges dictates that there are two bromines there. We know that magnesium is always 2+, and bromine is always -1. So it takes two of them. If we say magnesium bromide, we know it's this formula and nothing else. Plus, we're not redundant. We don't say magnesium dibromide because we already know it's dibromide. Magnesium bromide covers all our bases. And then our other example, calcium oxide, is that balanced? Calcium is an alkaline earth, so it's 2+, it's in the second column. Oxygen is that chalcogen. All these are 2-. So yeah, just 1 and 1 is all that's required to balance the charges. Okay, that's type 1. Type 2. It's still metal, non-metal. But now the metal could potentially have more than one charge. Variable charge on the metal. Now, where are those located? They're not the representative elements. Well, actually, there are a few. But these are fixed, these are fixed. These are fixed down to here, down to here, down to here. Well, these are metals. Most of the variable charge metals occur in the transition elements, except for those that we mentioned earlier. Zinc is always 2+, cadmium is 2+, silver's 1+. Right. The rest of them have multiple charges. So, for instance, if we had this one, silver is always +1, chloride is always -1, so that's a type 1 compound. Silver chloride. We don't have to say silver 1 chloride because that's the only charge it can have. So silver chloride is a type 1 compound, but the element above it, copper, is possibly two different charges, 1 and 2, I believe. So for copper, copper could be this one, or it could be that one. And in this case, this copper is a +1 charge. But in this case, it's a 2+ charge, right? Because this one's always -1. So that one has to be 2+ to balance if you write it that way. So this compound would be a type 2 compound. Now, how do we name it? Well, if the metal has a variable charge, we have to say what the charge is in the name. If you don't do that, then you can't go back the other direction and write the compound. You got to be able to go both directions. Write the compound from the name, write the name from the compound. And with no mistakes, there's no ambiguity. So when we write this one, we say copper, and then the chloride. But now we say that's the charge on the copper with a Roman numeral. So this one would be the same thing here, only now it would be Roman numeral 2. Okay? And you guys got it great. When I took chemistry as a student, we had to learn old-fashioned way. Instead of saying copper 1, this would be cuprous chloride. Instead of 2, this would be cupric chloride. And you had to know the difference, right? Cuprous meant 1, cupric meant 2. But if you tried that with a different element, like ferrous versus ferric, it would be different charges. The cuprous, it doesn't mean the same thing for the other elements. So I'm glad they made this change.
I'm glad they did too.
Yeah. So now there's no way to mess it up. It's copper 1 is a +1 charge on that copper. And that's type 2 compounds. Anytime the metal could possibly have more than one charge, and how do we know? Well, in your periodic table, let's see. Did I give you a copy of periodic table? I did give you a copy of periodic table. Did it have charges built into it? Okay, so you can look and see whether or not it's multiple charge or single charge, right? All of these should only have one charge. Most of these will have multiple charges. And then some of these also will have multiple charges. They're still metals because they're to the left of that zigzag. So tin could be a +2 or +4. Lead can be a +2 or a +4. So it would fall under type 2. Okay? And in any of those cases, you have to say what the charge is. Okay. We're going to skip this in the interest of time. I'm going to come back to this one. These are polyatomics. No, this is a good place for it. That I don't know if I gave you a separate one of these, but if you look in your no a handout I gave you for extra credit, naming compounds, extra credit. The last page is that, so you don't have to guess what the polyatomics are. We just have to define what is a polyatomic. A polyatomic ion is an ion that's composed of 2 or more elements, 2 or more atoms. Okay. They act as a single unit. And in fact, the atoms within the polyatomic are covalently bound. But the charge that's assigned to them is distributed over the entire polyatomic. They behave as a single unit. So when you write them in a compound, you can't break them apart. Like for instance, let's see, everybody's heard of sulfuric acid, right?
Yeah.
Okay. That's sulfuric acid. Well, as long as you put it in water, it's sulfuric acid. So this is a polyatomic. And you can find it here. These are sorted by name. These are sorted by formula. So if I say, okay, SO4, so I'll go down here to the S's. There it is at the bottom. This is derived from the polyatomic ion sulfate. And the polyatomics have names, and those names are fixed. This is always sulfate. And it's always a 2- charge. That's why we have 2 positive hydrogens attached to it to balance that 2-. But when you write the compounds, or name the compounds, type 1 or type 2. If a polyatomic is associated with a metal, all you have to do is say, is the metal fixed charge or variable charge? And then you use that in the name. Let's say a type 1 compound with sulfate as the anion. Okay, we need the metal as the cation. So let's make it potassium sulfate. Charge is 2 minus, and that's given here also, 2 minus. So we need, this is +1, so we need 2 of those. And if we say potassium sulfate, that's all you have to say. Because we know this charge, we know that charge. How about this one? What would that be? Well, if this is 2 minus, what does that have to be? It has to be 2 plus. So then we would say iron 2 sulfate. Okay, but iron can occur as a 3 plus ion also. So let's change it. Let's say I was wrong. It should be this one. So we need a 3 plus here. Okay. Now, how do you balance that one? Odd and even? Cross multiply, yeah. So a 3 has to come over here, but remember, polyatomic ions are a unit. So if you need 3 of them, you need also parentheses. Okay, and then of course 2 over here. So Fe2SO4 taken 3 times is the formula for that compound. Okay. There are a bunch of polyatomics in there. Some of them actually follow a pattern. For instance, well, first of all, I will say this. There's only one polyatomic that's a positive ion, that's a cation in this group, and that's ammonium. The rest of them are negatives. Right, here's the ammonium right there. And the rest of them are all negative charges. Okay, and you have some of them form groups. My favorite is the one that is formed with chlorine, and oxygen. And I always start here. That's chlorate. See, I'm going to run out of room. Chlorate. Now, if you take away 1 oxygen, you still got a negative charge. Take away 1 oxygen, that's chloride. Chloride. Take away another one. And we don't have any more endings that we can use, so we have to put a prefix on it. Hypo. Chloride. Right? Just like hypodermic under the skin. Hypochlorite is under chloride. Okay. And then we can add 1 more oxygen here. And that's perchlorate. So it's kind of like a family. We call that a homologous series because it's got the same elements in it. It's just they're different numbers. And you can do that with bromine, right? All the halogens. Bromine would be perbromate, bromate, bromide, hypobromite. We can do iodine, periodate, iodate, iodite, hypoiodite. You can cover a lot of them with just that simple sequence. And the reason I gave you this chart is because that's too many to memorize. So you just learn how to use that chart and learn how to recognize polyatomics. That's even a better skill. when you have a compound that's written with 3 elements or more, and one of them is oxygen, it's a pretty good guess it's going to be a polyatomic. For instance, acetate. Right? That's acetate ion. It's a polyatomic. If you add a hydrogen out here and put it in water, what do you have? Well, we're going to learn how to name that too. But if you have a 5% solution of that, you got vinegar. Okay, that's acetic acid. Well, we haven't got to naming acids yet, so I better move on to type 3s now. Type 3. Oh, that's right, you have to go. What? It's not time to pack up yet. Type 3 compounds, non-metal, non-metal. Okay. They're not ionic like these, but we're going to steal some naming conventions from the type 1s and 2s to help us with type 3s. We'll modify them a little bit. So binary compounds, we're going to write the first one as if it were a cation, but we know it's not. And then the second one as an anion and change the ME to IDE. Okay. Let's see, we did those polyatomics, right? Type 3s. Okay, so since they're not ions, there's no way that we can balance charges and write the compound with an unambiguous directive. So we have to, this case, we have to say how many of each one there is in the compound. For instance, how about this one? 2 nonmetals, right? This is carbon. This is oxygen, so we say oxide. But there are 2 of them. So we say di. Carbon dioxide. If there was only one of them, we'd say monoxide. Right? That's the one that kills, carbon monoxide. But notice we don't say monocarbon. If there's only one in this position, in the cation position, we don't say mono. It just doesn't sound right. But in the second position, we would say mono. Okay, so the question is, how do you know which one to put first? Well, if you're starting with a name, it's easy to write the compound because it's written in the convention cation, anion. So here we know to write carbon first and then dioxide. But if you're told to propose a compound with, let's say, sulfur and 2 oxygens, 1 sulfur atom and 2 oxygen atoms, which one comes first? Do we write it like this or like this? Well, the general rule to help you with that is if the element that is below and or to the left comes first, it tends toward the metallic side. That's the idea. Then it would come first. So we would use this one because sulfur is below oxygen. Or if we had nitrogen and oxygen, we'd put nitrogen first. It'd say oxide or sulfur oxide. In this case, sulfur dioxide. Okay, that's the convention. There are exceptions to that one, unfortunately. So follow that rule until we find exceptions and then just memorize them. They're not that many, fortunately. So you need your prefixes, the Greek prefix for numbers. Let's see, do we have a slide on that? Yeah, we do. Right? 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, like pentagram, 5-pointed star. 6 is hexa. 7 is hepta. 8 is octa, like octane rating for your gas. They call it that because octane is in your gas tank. Nona for 9 and deca for 10. They go past that, but that's as far as we're going. 10's good enough. So this one would be carbon dioxide, 2 oxygens. Carbon was first, sulfur hexafluoride. This one's got 2 nitrogens, dinitrogen, tetroxide. Notice we dropped the A. Right. Chemists have sensitive ears too. If you say tetroxide, it just doesn't sound right. Drop the A and just say tetroxide. Okay, so how do you know what to do? Decision tree. If you have a compound that's written a certain way, first you look and say, is it metal, non-metal, or is it 2 nonmetals? If it's 2 nonmetals, you go straight to this one for naming. If it's a metal and a non-metal, then you have to say, all right, what's the character of the metal? Is it fixed charge or a variable charge? Now that's not variable charge within the compound. Once it's written, its charge is fixed, but it has the potential for different charges in combination with the anion. That's what you're looking for. And if that's the case, then you use type 2 convention. If it's it's a fixed charge, you got type 1 off to the races. Okay, that's how you decide. Now for naming acids. Unfortunately, alchemists beat us to the punch. They knew several mineral acids long before modern chemistry came around. They knew how to make hydrochloric acid, they knew how to make nitric acid, they knew how to make sulfuric acid. So we were sort of stuck with that one, and we had to blend that naming convention into some order. And this is the order. Acids will always start with a hydrogen, at least one, sometimes more. So that's the clue. Even if there are other hydrogens in the molecule, it will always start with 1 or more hydrogens. Then you look for the rest of the molecule. Is there an oxygen there? If there's no oxygen, then you start the name with hydro. You start it with this. Then you follow it with whatever the anion happens to be. And if it's an ide, then the ending changes to ic. So this would be, if that were the compound and that we weren't naming it as an acid, this is HCl gas. Right? It's a pure gas. It would be hydrogen chloride, right? Hydrogen, and then change the ending to IDE. If you put it in water, that's what AQ means, aqueous. Put it in water, then it becomes the acid. And in that case, you change the name, and it's hydro, chloride becomes chloric, hydrochloric. Acid. Okay, that's if there's no oxygen there. You always start with a hydro. How about polyatomics? Remember, most of the polyatomics, let's go back. Most of the polyatomics have oxygen in them, don't they? There's some right down there. There's one that doesn't. Cyanide. Right? So if we use this naming convention for cyanide, that works. There's no oxygen there, right? So what would this be? Let me make some room here. What would this be purely as a compound? We haven't put it in water yet. Purely as a compound, this would be hydrogen cyanide. Right? Hydrogen cyanide. It's deadly, by the way. Now, if we put it in water, it becomes hydro cyanide cyanic acid. Okay? Because there's no oxygen there. We started with hydro. Okay, now what if there's oxygen there? If you've got oxygen, then you do not start with hydro. If there's an oxygen there, don't say hydro ever. So let's use this one. What would it be if it were not dissolved in water? Just purely naming convention that we came up with before. It would be hydrogen nitrate. Right. That's the nitrate polyatomic ion, hydrogen nitrate. If we're going to name it as an acid, then we throw this out, we keep this, and we change that to ic. Aches become ics. So we just say nitric acid. Okay. While we're on the topic, what if instead this is, instead of that, it's HNO2 aqueous. Right. Remember the chlorate, take away an oxygen, chlorite. This is take away an oxygen, nitrite. So this would be hydrogen nitrite. So in that case, the eights become ics and the ites become us. So this would be in aqueous solution, nitrous acid. Okay. And there's our acetate ion. 8 becomes ic. There's oxygen there, so we say acetic acid. 5% acetic acid is vinegar. Okay, there's our us. Sulfate, 8 becomes ic, sulfuric acid. We change the name just a little bit because it sounds better. Instead of sulfate becomes, we wouldn't be sulfic, just doesn't sound right. Sulfuric, sulfurous for this one. Okay, so there's your decision tree if you need one. Let's see.
How are we doing on time? Okay. Let's see. I want to be sure and get to okay, we're still naming compounds. All right. Okay. I wanted to be sure I wasn't leaving some important topic out.
So now we're just honing our skills. Okay, which of the following compounds is named incorrectly? Well, what do we got here? We got a metal and a polyatomic, which is the same as a metal nonmetal. So potassium is fixed charge. We use a type 1 convention. Potassium nitrate. That's it. That's all you need. It's unambiguous. Titanium. Where does titanium come from? Right there. I don't know if you can see it from there, but there's several charges right in there. Titanium is a type 2. Would be a type 2 in this compound. So you have to say the charge on titanium. Well, let's see. If this is titanium oxide, what's the charge on titanium? Oxygen is 2 minus, right? It comes from here. 1 minus, 2 minus, 3 minus. Oxygen is 2 minus. So that means we have to balance a 4 minus total charge for the oxygens. So titanium would have to be 4 plus, right? That's wrong.
That'd be 4 instead of 2.
Yes. Titanium, Roman numeral 4, oxide. How about this one? Hydroxide. That's a polyatomic. If you see a compound written like this, and it's got parentheses around it with a subscript, you know that's a polyatomic. That's the only way it can be. It can't be anything else. So what's the charge on, this is hydroxyl polyatomic anion. It's a -1 charge. So 4 minuses means that 10 has to be a 4 plus, which is correct. 10,4 hydroxide. How about this one? Phosphorus and bromine, type 1, 2, or 3. Type 3. There's phosphorus, non-metal. There's chlorine, non-metal. So you use a type 3 convention. That means phosphorus, pentabromide, and it's done. No charges involved there. How about this one? CR04. We got 1, 2, 3 elements and 1 of them is oxygen. Probably a polyatomic in there somewhere. And the polyatomic, except for this one, the polyatomics are going to be in the anion side, always. Unless you put that in there. And then it's going to occupy the cation side. That's easy to spot this. But if you have oxygen in there, then this polyatomic is going to be in the anion side, and that's CrO4. You look it up, it's chromate. Okay? And it's a 2 minus charge. So 1 chromate, 1 calcium, and calcium is a fixed charge metal. So this is correct, calcium chromate. Okay. Sometimes you can get 2 polyatomics together. If you have ammonium, and then virtually any one of those other anions will bond with it. And you can have a compound with 2 polyatomics, right? You know this one? Any farmers in the family? No? Ammonium nitrate, great nitrogen fertilizer for your crops, corn, wheat, whatever. It also makes a good oxidizer for a bomb. Ammonium nitrate, 6% fuel oil, and a blasting cap or a stick of dynamite. And you can bring down the Alfred P. Morrow building in Oklahoma City with a truckload of that stuff. That's why the government watches ammonium nitrate sales really close. If you buy lots of ammonium nitrate, you're a farmer, then you've got you're registered and you've got a permit, and the government's okay with that. Right? But if you got a name that sounds sort of Arabic, and you walk into a feed seed store and want to buy, 10 tons of ammonium nitrate, they're probably going to tell you to get lost. Okay. I mentioned this earlier. The atoms in the group of the polyatomic are covalently bound. So they're very, very tightly bound together, and they share that charge over the entire group. In other words, when we write this as the sulfate polyatomic ion, we're not saying that that oxygen has 2- charge. We're saying that that whole group distributed over its entirety is 2- charge. Nobody has dibs on it. That's why when you write it in a compound, if you need more than one of them, you got to use parentheses. Okay. I've said all this stuff before. Generalizations. Okay. Let's see, we might be close to the end. All right, this is important. You cannot modify the polyatomic to make it balance, to write the compound. Once the polyatomic is there, the only way you can have more than one of them is with parentheses. Okay. Going the wrong direction. There we go. Ammonium carbonate, okay. So what the government likes to see used as a nitrogen fertilizer now is urea rather than ammonium nitrate. They don't even like to see potassium nitrate or sodium nitrate because the nitrate is the oxidizer that makes that bond work, not the ammonia, the nitrate. So they like urea is a better choice. It's just two bonds here with that oxygen. So that's urea. And you can't use it to make a bond, but it's got nitrogen in it. Some farmers actually prefer a liquid ammonia. It's pure ammonia. Call it anhydrous. You have to carry it around in a stainless steel tank, right? And leak through anything else. And you have to have special equipment to inject it under the ground where it can react with water, right? Because as soon as it comes out that nozzle, it wants to be a gas. And if you do it above ground, it's gone. So you inject it under the ground. It combines with the water. Now it's stable in there. It also creates a nice big kill zone. So any microorganisms, any animals, any plant roots in that zone are dead until it dissipates and they have a chance to reinvade. But it's very efficient fertilizer. Right? You got that nitrogen and just what, 3 little hydrogens, 1 atomic mass unit each. Nitrogen's 14, so there's a lot of nitrogen in there. It's a compact source. It's a good source if you've got the equipment for it. Okay, and we're going to skip those. Concept question, correct information. Let's see. What is this? You ever do any baking? Quick bread? That's sodium bicarbonate, baking soda. Makes gas when you heat it, but you have to add a little acid to it. So baking powder has the acid built in, only it's dry. So it won't react until you add moisture, add water, and then heat it up and poof, makes lots of gas and makes your biscuits rise or your cake rise or whatever. But this is, the polyatomic ion is named hydrogen carbonate. Bicarbonate is the old way to name it. But you'll still see it on food labels. Food labels are notorious for having old names.